السلام عليكم ورحمة الله وبركاته. So this is going to be our last lecture, where we will conclude chapter 15 and say some things on chapter 8 as well. So steady uniform flow, by saying uniform flow, the velocity is constant in the flow direction and the shape of the channel and the depth is the same throughout the section. And slope equations shows that for uniform flow, the slope of hydraulic grade line will be the same as the channel slope because the velocity and depth are the same. This, I think, we discussed before. And the hydraulic grade line, and thus the slope of water surface, is controlled by head loss. If you remember, this is the hydraulic grade line. This is the energy grade line. Remember in Bernoulli equation and as well as the energy equation. For uniform flow, they are all parallel. Energy grade line, hydraulic grade line, and the bed slope, which is S naught, because the depth is constant throughout. Okay. So for uniform flow, you need all these to be true. The cross-sectional shape has to be constant, the depth has to be constant, and the velocity has to be constant. Okay, all these have to hold. But you see, in this case, y1 is not equal to y2 because the depth is increasing with distance. Okay, and hence this is not a uniform flow. And to unify Reynolds numbers for open channel and pipelines, scholars presented the following. You remember we defined hydraulic diameter when discussing about pipe. Okay, so and we define hydraulic diameter DH as 4 times area of cross section over water perimeter. Okay, in open channel flow, the area of water perimeter is given a special name hydraulic radius, which is area over weighted perimeter. So that implies that the hydraulic depth is simply 4 times the hydraulic radius. Ordinarily, the hydraulic diameter. Ordinarily, diameter is 2 times the radius, but hydraulic diameter is 4 times the hydraulic radius. Okay, so the hydraulic diameter for pipes and hydraulic radius for open channel. And in this case, we can replace, in the Reynolds number, you use VD, where D is the hydraulic diameter, okay, which is pipe diameter in case of pipe, circular pipe, okay. So it means here we will replace the 4R, okay, over more, okay. And for that, for laminar flow in open channel, you divide this by 4 in that case. Okay, if you remember, this has to be less than 2000 for pipe flow. So when you divide by this 4 here, so that will give you 500. So for open channel flow, the Reynolds number should be less than 500. Okay, and when you divide 3000 by 500, you will get 750. Okay, so greater than 750, you have turbulent flow. In between 500 and 750, you have a transition zone. And in some texts, they use up to 1,000 because they use the upper limit to be 4,000. Okay. So using this relation is very useful when determining friction factor for channels. Okay. Because when using the Das-Weisbach equation now also in the diameter, instead of using the diameter or the hydraulic diameter, we will use the hydraulic radius, as we are going to see now. Yes. So steady uniform flow, the slope of energy grade line equals the slope of the channel bed. And recall the head loss equation. See this. Recall the head loss equation using the Das-Weisbach equation. We replace D with 4R. D is equal to 4R. Okay. So we replace D with 4R. Okay. So here the head loss by unit length, which is this, the bed slope, or is actually the friction slope. Okay, which is parallel, because this is called the friction slope SF, which is equal to S naught for uniform flow. Okay, so SF is actually the frictional head loss per unit length of the pipe. This we defined before, if you remember. So the slope now is given by this. Okay. And when you try to make V the subject of the formula, because if you replace this with S naught, okay, and try to make V the subject of the formula, okay, you will have it to be 8 GRH over F, okay, times S naught. Okay, it is from here that we move to this. Okay, and then this we call the Chesi formula. Okay, because HG over F are all constants, so they can be replaced with a constant C into root R S naught. This is called Chesi equation, where C is the Chesi constant, which is square root of 8G over F. Simple, okay, which is called Chesi constant. Okay, so meaning we can find the velocity in open channel by knowing the bed slope and the hydraulic radius. The hydraulic radius is just dependent on the dimension of the channel, okay, area and the perimeter, weighted perimeter. Simple. Okay, let's take a simple example here to apply the Chesi equation. So from the Das-Weisbach equation, you can get the Chesi formula and apply the Das-Weisbach equation to find flow rate in a rectangular open channel. So here we are to estimate the discharge of water that a concrete channel 10 feet wide can carry if the depth of flow is 6 feet and the slope of the channel is 0.0016. So here we have the bed slope. So here, assumption, we are assuming uniform flow. Okay, we are assuming uniform flow. And for concrete, the properties, the roughness size, this is the roughness, and this is the kinematic viscosity. And to find the discharge, we use VA. To find the velocity, we use this formula to find the velocity. Okay, and here we know S naught. We can find RH, which is the weighted perimeter, which is area over weighted perimeter. Okay, for rectangular channel, the area is just B times Y. The weighted perimeter is all the sides that the water is in contact with, which is B plus Y plus Y, which is B plus 2Y. Simple. So this is the hydraulic radius. Okay, and to find F in equation B, use an iterative approach with the Moody diagram. Okay, this is a case 2 problem in chapter 10, which we discussed, where we assume, the value of the friction factor and then evaluate the Reynolds number and the roughness and the relative roughness, then go back to Moody diagram to find F and compare the two Fs. If they agree, if they are equal, we stop. If they are not, we revise the new F. Okay? So, as usual, we calculate the relative roughness. And to calculate the relative roughness, you see here, instead of using D, we use 4R. Okay? Because D in that case is diameter, which is equivalent to the hydraulic diameter, which is now 4 times R. Okay, so this is very important to note here. Okay, so this is our relative roughness. Okay, and use the value of this as a guide to estimate F. So we now estimate F. We assume F to be 0.016, and then based on this, we determine the velocity, okay, using this formula because there is F here. You can see it, okay? So we determine the velocity and the Reynolds number, okay? And then we now go to the Moody's diagram to read using the this new value of RE and the roughness, relative roughness, read F, okay? So F is 0.06, which is the same as the previous one that we assumed. So this is our correct value of F, and this is the correct value of the velocity in that case. Okay, and then we can simply find the flow rate. So we use iterative procedure to find F. Okay, most of the time if it is not given. Okay. Now this we discussed before, in the pipe flow, for concrete pipe, this is the KS, okay, 0.323. Here we took KS as 0.005 feet. Okay, it is within the range. Okay. Now, special case for determining F for rock-bedded channels. Okay, so for rock-bedded channels, use this formula to determine F, where F is the friction factor. D84 is the diameter of rock that at least 84% of the rocks are smaller than. Okay, so the diameter of the rocks that 84% of the rocks are smaller than. Okay, which is D84. Okay, and in this example here, resistance coefficient for boulders. Boulders are big rocks, okay? Big size, bigger than gravels. So here we are to determine the value of the resistance coefficient, which is F. F has several names: friction factor, resistance coefficient, there's Westbach coefficient, and all that. For a natural rock bedded channel that is 100 feet wide and has an average depth of 4.3 feet, the D84 size of boulders in the stream bed is 0.72. So here we have the width of the channel and we have the depth. So we can find the hydraulic radius, isn't it? We can have the hydraulic radius. And here, since it is wide, because for wide channels, the hydraulic radius for rectangle is by over b plus 2y. But for wide channels, b is far greater than y. Okay, for wide channels, the width is far greater than the depth. Okay, so you have this term to be negligible, 2y, when added to the breadth. Okay, so this reduces to just by divided by b. Okay, so b cancels b, which is y. Okay, so the hydraulic radius is approximately equal to y. This is applicable for wide channels. So you can see the channel width is 100 feet and the depth is 4.3 feet, very small. Okay, so the hydraulic radius is just taken to be the depth of the channel. Okay, so to find F, we use the formula. We just plug in the values straight ahead and get our friction factor. Simple. Still on steady uniform flow, although using previously using previous methods. Okay, 25. Using previous methods for determining the flow characteristics at open channel using KS and Reynolds number is recommended by researchers. However, engineers prefer to use Chasey equation and Manning equation. Okay. Chasey equation and Manning equation, and they are limited to uniform flow and normal depth. Normal depth is the depth of flow for uniform flow. Okay, we call it normal depth, YN. And we use the Chasey equation. This is the Chasey equation, the flow rate. We derive the Chasey equation, if you remember, from the Das-Weisbach equation. Okay, although we derived it in form of velocity V equals C root R S naught. Okay, so the flow rate, you will have A added to it. And the Manning equation, okay, which is empirical, is an empirical formula. It's 1 over n. N is the Manning's roughness coefficient, which varies depending on the roughness of the channel. Okay, A R to power of 2 over 3, S naught to power of 1 over 2. These are the values of the Manning's constant. Okay, which is different for different channels. Line canals, you can see, on line canals, you can see they are having relatively higher coefficient on line canals because they are rough, they are rougher, and natural channels as well. They have the highest. Natural channels have the highest because the channels has rough bed slope. I mean bed rough surfaces. So the Manning's rough, that's why it's called Manning's rough or roughness coefficient N. And to apply the Chasey equation to find Manning's N for flow in channel. Here, if we have a channel with boulders, has a slope of 0.003 and is 100 feet wide and has an average depth of 4.3, similar to the previous problem, and is known to have a friction factor of 0.13. You know, we determined the friction factor in the previous example. Now, what is the discharge in the channel, and what is the numerical value of the Manning's N for this channel? So we want the discharge and Manning's N. So S naught is given B, Y, and F. Because it is wide channel, R is approximately equal to Y, okay, because the channel is wide. Now, we use the Chasey's formula to find the velocity. We have F, we have RH, we have S naught, okay? We found the velocity and the flow rate as well, okay? And then to find the Manning's N, we go back now because now we know the flow rate using the Chasey's formula. So all other parameters, the area, RH, S naught are known. So we can determine N. Simple, okay? But this is the Manning's for roughness coefficient for this channel. Yeah, this is the yeah. Let me take it back to the presentation mode. Okay. Now, best hydraulic section for uniform flow. Best hydraulic section is the channel geometry that yields a minimum weighted perimeter for a given cross-sectional area. Okay. Therefore, it yields the least viscous energy loss for a given area. So when you have the minimum weighted perimeter, it means you will have less viscous or friction effect. Okay, so it gives least viscous energy loss for a given area. Okay, so that we call the best hydraulic section. And when you consider the quantity A r to the power of 2 over 3 in Manning's equation, is referred to as section factor. Okay, for normal flow or for uniform flow, we call it Zn. Okay, section factor for uniform flow. And for uniform flow, the section factor can be expressed as this, because hydraulic radius is A over P. Okay, and for a channel of given resistance and slope, the discharge will increase with increasing cross-sectional area. Okay, but decrease with decreasing weighted perimeter. Okay, so the discharge will increase because when you look at the Manning's formula, it is 1 over n A r to the power of 2 over 3 s to the power of half. Okay, so, and don't forget r is A over P. So when A increases, the flow rate increases. What about when P decreases? When the weighted perimeter decreases, or when the weighted perimeter increases, because it is denominator, so Q decreases, the flow rate decreases. Okay, so that is why the discharge will increase with increasing cross-sectional area, but decrease with increasing weighted perimeter. So, and we don't want to decrease the discharge, so we need to minimize the weighted perimeter to make it the barest minimum. Okay, because once it increases, the discharge will decrease. Okay, so the concept, that is the conceptual, idea behind the Beck's hydraulic section. For a given area and a channel and a given channel shape, for example, the rectangular section, there will be a certain ratio of depth to width for which the section will be maximum. Okay, this ratio is the best hydraulic section. Okay, so there will be a ratio of depth to width for which the section factor will be maximum. Okay, and we want to maximize the section factor. Don't forget the section factor is simply AR to the power of 2 over 3. Okay, AR to the power of 2 over 3. Because as the section factor increases, it means the area increases. Okay, and as the area increases, the flow rate, the discharge increases. Okay, so there is a certain ratio of the depth to width for which it is maximum. We will take example. That's all we for several types of channel cross sections, the best design is shown in this figure and summarized in the following table. Okay, you have the cross section for rectangular. The optimum width B is 2 times the depth. Okay, and this is the area, and this is the weighted perimeter, and this is the hydraulic diameter. Okay, DH. And for trapezoidal section, this is the optimal width. For semicircle, this is the optimal width. Let's take this example to demonstrate how did we get this, because it implies B is equal to 2y. Okay, how did we get the optimal width? Okay, we'll demonstrate that of a rectangle, but the same procedure applies for all other sections. Okay, we want to determine the best hydraulic section for a rectangular channel with depth y and width b. Okay, so this is the area and this is the weighted perimeter. Okay, so this is the weighted perimeter, and we want to minimize. We differentiate p with respect to y and set the derivative to 0, because that is when the weighted perimeter will be minimum. Okay, so we are minimizing p. So to minimize P, we differentiate P with respect to Y, okay, and equate it to 0. And when we equate it to 0, A equal Y squared. A equal 2Y squared, okay? And when we express the results, you remember A is equal to BY. And now if we substitute A here as BY, so Y is B over 2, which gives B to be equal to 2Y. So this is the base hydraulic section for a rectangle, okay? You can do the same thing to prove for trapezium, for trapezoidal section, or for semicircle. By following the same procedure, express the weighted perimeter, you differentiate it, equate it to 0, and then substitute the area to get the relationship between the breadth, the depth in this case, the width, okay? In this case, like for a circular section, the width is going to be the diameter, okay? Okay, or the depth for a semicircle. So this is the depth, and the width is going to be the diameter, okay? The width, which is 2 times the depth. For trapezium, the width is 2 over root 3 d, okay? And this is for rectangle. The width is 2d. Now, uniform flow in culvert and sewers. Let me drink water. Sewers are conduits that carry sewage, okay? There are also pipes, okay? They are pipelines, okay? But they are called sewers because they carry sewage, simple, okay? The sewers are just pipes, okay? Can carry liquid domestic, commercial, or industrial waste from household, businesses, and factories to sewage disposal sites or sewage treatment plants or wastewater treatment plant. And these conduits are often circular in section, but elliptical and rectangular conduits are also used, okay? And they also flow as, open channel flow because they don't flow full. Designed to carry the maximum design discharge, flowing full or nearly full, okay? Normally they are designed flowing nearly full, okay? At discharges less than the maximum, sewers will operate as open channels because they have open surface, free surface exposed to the atmosphere. We discussed before yesterday. And sewage usually consists of about 99% water and 1% solid waste. Okay, so it's basically fluid flow. Okay, 99% water and 1% solid waste. Since most sewage is so dilute, it's assumed that it has the same physical properties as water. For purposes of discharge computations, you can see 90% water, just 1% solid waste, okay? So our assumption that, using it as, using the properties of water for purpose of discharge computations is justifiable in this case. And the minimum velocity of about 0.6 at times when the sewer is flowing full, okay? So we establish uniform minimum velocity of 0.6. And this condition is met by choosing a slope on the sewer line to achieve the desired velocity. Why? Because the slope controls the velocity. You have seen in the Manning's equation, V equals CRS. So the bed slope controls the velocity, okay? And the minimum, why do we have minimum velocity? To avoid deposition, because we have 1% solid waste. That solid waste, if you don't have adequate velocity to wash it away, they can deposit on the bottom. And when they keep on depositing and piling from the bottom, they will reduce the effective carrying capacity of the pipe, okay? Thereby causing problems, okay? So that's why you need some minimum velocity, or we call it self-cleansing velocity, to clean the sewer, to clean the solid waste, to avoid deposition of the 1% solid waste, okay? And of course, culvert. is under a highway embankment, conveying water. When you have like a roadway, this embankment, this is a roadway, and this is culvert, transporting water from one end to the other. Now, this is a typical household. You have wastewater. If it rains, you have the roof drain connection, okay, which is collecting the rainfall from the rooftop, okay, and connected to foundation drain, okay. And then this is uncapped clean out, okay. So the waste will be collected, which is the sanitary, the um, storm wastewater, okay. This is storm wastewater, and then you also have wastewater from the toilets, which is the sanitary wastewater, okay. So these are inflow sources and these are infiltration sources, okay. So here you have house broken lateral, so which is conveying the wastewater, faulty lateral connection. This is connected to the pipe. You see the sanitary sewer, okay. And this is storm sewer collecting, rainwater, rainfall, okay, which connects water by the side of, the roads. You might have seen these, shapes, okay. They drain water through a storm sewer, okay, a storm sewer cross section. And then this that drains the household sanitary sewer, because it consists of the storm sewer as well as the sanitary sewerage from our toilets, okay, when we flush, okay, when we bath, all this, okay, they constitute the sanitary sewer, the sanitary sewerage. And this is called manhole cover or frame, okay, which is like inspection chamber, okay, where you have, the pipes changing in size or slope. You need to install a manhole, okay, which is like a node in the case of pipeline, okay, where pipes are meeting. And there's problem when you have cracked or broken pipe, because it will leak out. It will leak out if there is any fault, okay. Now let's take this simple example about sizing a round concrete sewer line. Okay, how do you size it? Because that is the basic design, the slope and the size of the sewer line. Here it says a sewer line is to be constructed of concrete pipe to be laid on a slope of 0.006. If the Manning's N is 0.013 and if the design discharge is 110 cubic feet per second, then what size pipe commercially available should be selected for a full flow condition? So full flow, it means there is pipe flow, okay, it's flowing full. And what will be the mean velocity in the sewer for these conditions? It should be noted that concrete pipe is readily available in commercial sizes of 8-inch, 10-inch, and 12-inch diameter, and then in 3-inch increments up to 36-inch diameter. From 36-inch diameter up to 144. The sizes are available in 6-inch increments, meaning from 12-inch to 36 is available in 3-inch increment, that is 12 plus 3, 15. 15-inch, 18-inch, 21-inch, up to 36. And from 36 to 144 is in 6-inch increment, that is 36 plus 6, 42. 42-inch, 48, 54, up to 144. So we can only use the standard pipe size, okay? And the goal here is the pipe diameter should be large enough to carry design discharge that flows, that allows that the velocity is at least greater than 2 feet per second at full flow condition. Okay, so this should be the minimum flow velocity, 2 feet per second. And here we'll use the Chesney equation, to find the section factor. Okay. In this case, we can find the section factor using the Manning equation. Okay, you can see this is the section factor. Okay, every other thing, flow rate is known, this is known, bed slope is known. Okay, and here assume atmospheric pressure in the pipe. So we are not as, so it's still flowing, you know, as open channel flow. Okay, so it's not really a pipe flow, because for us to apply the Chasey-Amanis equation, it has to be an open channel flow, not pipe flow. They are only applicable to open channel flow. So here we made the section factor the subject of the formula, and from there, this is the hydraulic radius, okay, which in this case is 2/3. Okay, we express the section factor in area and weighted perimeter. Okay, and for a pipe flowing full, the area is the pipe area, I mean pipe diameter, sorry, pipe section, pi d squared over 4, and the weighted perimeter is the circumference of the cycle, which is pi d. Okay, so if we substitute here to find d is 47.8 inch, but 47.8 inch is not among the commercial size diameter, so we use the next commercial size larger, which is 48. Remember, from 36 it increases by 6 inch, so that 6 inch you have 42 and then 48. Okay, so this is 47.8, so we use the next one, not the one before it. That's very important, because so as to be able to contain the flow. Okay, so we use d to be 48 inch. Okay, and then once we determine the pipe diameter, then we can determine the area now. So this is the area for pipe flowing full. Okay, so we started with as if it's not flowing full, we apply the Manning's equation to find the diameter. Then for pipe flowing full, this is the area. And to verify that the velocity is having a minimum velocity of 2 feet per second, we use the given area now to see if the velocity will be greater than 2. And we found the velocity to be 2.19, which is just to ensure, because for design purposes, even for pipeline, after designing the pipes that will convey water to your households and all that, you need to check that the minimum velocity is satisfied, as well as the minimum pressure head. Okay, minimum velocity and minimum pressure head, they are all satisfied. You need to make sure that they are satisfied, you know, in the pipeline. So this is very important. So now for culverts, a culvert is a conduit placed under a field, such as a highway embankment. Embankment, you know, this is the embankment, you know, just like, you know, highway, you have a dam and all that. Okay, so this is an embankment, protrusion above the earth's surface. Okay, and it is used to convey stream flow from the uphill side of the field to the downhill side. This is the uphill, this is the downhill. This is upstream, this is downstream. A culvert should be able to convey runoff from a design storm without overtopping. Okay, when it rains, it should be able to convey to drain the water in the area without overtopping. Okay, without water filling it and even, let's say, coming onto the roadway, and without erosion of the field at either the upstream or the downstream end of the culvert. The design storm, for example, might be the maximum storm that could be expected to occur once in 50 years at the particular site. Okay, so for design, usually we design for the maximum, for the worst case scenario. So that is why we look at the maximum storm once in 50 years. Okay, so we design our culvert to be able to handle such storm if it were to recur. Okay, and the flow in a culvert is a function of many variables, including the cross-sectional shape, that is circular or rectangular, the slope, the length, and the roughness, entrance, design and exit design. And flow in a culvert may occur as an open channel throughout its length. It may occur as a completely full pipe, or it may occur as a combination of both. Now let's look at some simple example of the culvert design here. Here you have a 54-inch diameter culvert, which is laid under a highway embankment, okay, and has a length of 200 feet and a slope of 0.01. This was designed to pass a 50-year flow of 225 cubic feet per second under full flow conditions. Under full flow conditions. For these conditions, what head H is required? Okay, which is this one. You can see the head H. What head H is required? When the discharge is only 50 cubic feet per second, will the uniform flow depth, what will be the uniform flow depth in the culvert? Okay, assume N to be 0.012. Okay, so you can see here the height H required between the two free surfaces when flowing full. And when flowing full, it will flow as a pipe flow, okay, because all the spaces within the culvert will be filled up, okay. And we are to find the uniform flow depth in the culvert when the discharge reduces from 225 to 50, okay. So here we use the energy equation between the two ends, okay, to account for head loss, because we want to find the elevation difference, okay. Like this is H, the elevation difference between the two pools. And to find the head loss HF using this, the bed slope is equal to HF over L, okay. So that is assuming uniform flow, okay. So in this case, we use the energy equation, okay. We don't have any pump or turbine, so we only have head loss, okay. And because they are all exposed to the atmosphere, so the pressures the same, atmospheric 0, okay. And the velocities also for the 2 points 0, okay. So the head loss is simply due to the elevation difference, okay. So the head loss is simply H here, which is Z1 minus Z2. But we also, if you remember, the head loss is sum of the pipe head loss and the minor head loss, or the component head loss, isn't it? This we did before, okay. So the major head loss is the frictional head loss, and the minor losses, you have head losses occurring at the culvert entrance and exit, as well as over the length of the pipe, okay. At entrance and exit, there are minor head losses. Within the pipe is a major head loss, okay. So you have pipe head loss plus entrance head loss plus exit head loss. So you have exit and entrance and the pipe head loss, which is the frictional head loss. These are the coefficients for the entrance and exit, okay. And then to find the pipe head loss, which is the frictional head loss, we have to use this formula now, okay. Now for the pipe head loss, if you look at, okay, slope. Here, this is the Manning equation, okay. And for the Manning equation, we have the flow rate, which is given from problem. This is the area of the pipe, okay, which is provided. And to use the Manning formula, we use hydraulic radius, which is area of a weighted perimeter, which is simply D over 4. Okay, so, and then this is the bed slope, which is HF over L. Okay, we want to find HF. We want to find HF. This is the length of the pipe. So the only thing unknown here is the frictional head loss, which we found. Okay, and we can use now continuity equation to find the velocity in the pipe. And once we do that, we just go back to substitute the velocity to substitute the pipe head loss. Okay, which is exactly what we did here. So this is the difference in head between the upstream and downstream section. Now the next question is to find the depth for uniform flow when Q is 50 cubic feet per second. We still go back to the Manning equation. Okay, still go back to the Manning equation, and in this case we determine the section factor. Okay, because it will not flow full in this case. Okay, it will be an open channel. So values of the area and the hydraulic radius will depend on the geometry of the partly full pipe. Okay, it will depend on the geometry. This is the diameter. This is, if this is the depth of flow. Area A, if angle theta is given in degrees. Okay, what is the area? Okay, so the area here is simply this. Okay, this is the area for full cycle. Okay, and then minus the remaining portion. Okay, and don't forget the weighted perimeter is pi d. Okay, the weighted perimeter is pi d. So A over P. So this gives our hydraulic radius. And when you substitute the discharge equation, we find theta to be 70. And then to find y is simply this minus that portion. Okay, which is simple geometry. Okay, this is the radius, okay, minus the other portion. Okay, so this is the depth for uniform flow. Now, uniform flow, you have the depth remaining constant with time at every section. When the depth is changing, now you have two things. Does it change abruptly? Does it suddenly change? Or does it change over some distance? If it changes over some distance, we call it gradually varied flow. If it changes suddenly, okay, we call it rapidly varied flow. Okay, if the depth of flow changes abruptly, okay, suddenly, we call it rapidly varied flow. And rapidly varied flow is analyzed with the energy equation as well, presented previously for open channel. Because for rapidly varied flow, you have energy loss, which is accounted for in the energy by the energy equation, and with additional assumption that the channel bottom is horizontal. Okay, that is S naught is 0, because normally the channel bottom is very small. You see, 0.001, very small. Okay, so the assumption is that the S naught is 0 and the head loss is 0. So if this holds true, okay, you have the energy equation reducing into this. Okay, if S naught is 0, there will be no term in elevation because Z1 is equal to Z2. Okay, then the head loss, which is assumed to be 0, it disappears in the term. And the sum of the depth and the velocity is called the specific energy. It has a special name called specific energy. And note that specific energy has dimensions of length. Okay, that is, it is a head term. Okay, so the equation states that the specific energy at section 1 is equal to the specific energy at section 2, or E1 is equal to E2. And this is the continuity equation which holds. So if we substitute V as Q over A, we have the specific energy expressed in terms of Q and A. And then this is for 2 points, point 1 and point 2. If we try to plot this formula, you can see you have the first portion y. This is E equal y. Okay, E equal y. And then you have the second portion, which is for the velocity head, v squared over 2g, which is this. Usually the plot is like this. Okay, so this is for v squared over 2g. Okay, and this is E equal y. Okay, and then when you add this to y plus v squared over 2g, it will give you this one, this blue line. Okay, it will give you the blue line. A critical flow occurs when the specific energy is minimum for a given discharge. The specific energy is minimum at this point, because this is the axis for specific energy. Okay, when it is minimum, you have critical flow occurring. And when it is minimum, we can find some relationship. What is the depth when it is minimum? This is the specific energy equation. We can differentiate it with respect to y and equate it to 0, because if it is minimum, dE dy will be 0. Okay, the slope is going to be 0 in that case. Okay, because the specific energy is constant. Like when you want to find the slope here, you can see E1 equals E2. Even though the depth changes, there are different depths. dE is not equal to 0. Sorry, dy is not equal to 0, but dE is equal to 0. Okay, so it is minimum in that case. And when you differentiate this, you got this. Okay, and when you simplify it, we have hydraulic depth, which is equal to the area over the top width. Okay, and when we substitute the hydraulic depth, find it to be v squared over g. And that means v is 1 is equal to v over square root of gd. Okay, which is Froude number. Okay, it's a dimensionless number. You remember we talked about the what is it called? We talked about the Reynolds number before. Okay, so Froude number is simply O square is v over gd or gy. Okay, therefore it is shown that the Froude number is equal to unity when critical flow prevails. Okay, it's equal to 1 for critical flow. And that's why here this is vc, the critical velocity, and the depth is the critical depth here. This is the critical depth. Okay, but after that, for every value of the specific energy, you have two depths: supercritical depth and subcritical depth. supercritical depth is smaller than the critical depth, but subcritical depth is bigger than the critical depth. Okay, this happens usually like when you have a weir. Let's say you are hanging. So the flow will be like this, and here you have YC, and this is Y1, and this is Y2. This is subcritical depth, critical depth, and supercritical depth. The velocity is higher here. Okay, it is higher than here because there's reduction, because of the reduction in cross section. Due to this, there's velocity head. Okay, v squared over 2g. Okay, so the flow is accelerated. So yc is greater, and then here is accelerated further. So y2 is greater than yc, greater than y1. So for critical depth, yc, the critical depth is q squared over g to the power of 1 over 3. Q is flow per unit width of the channel. Okay, q over b. Capital Q over B, which is the flow discharge per unit width of channel. Okay, so this relationship is very important for critical flow. Okay, in water engineering, we'll explore more about critical flow. Okay, we'll talk more about it. We'll analyze it. We will do measurement. We will do some experimental work. I mean, some laboratory experiments to measure the critical depth, and use that in the flow measurement. Okay, or measure using hydraulic structures. Okay, like weirs. Okay, broad crested weir and the Venturi flume. Calculating critical depth in a channel. Don't forget about the normal depth or the uniform depth of uniform flow. Now we are moving to critical depth. Okay, although we will not really, like I said, say so much or dwell, treat this deeply. Okay, but at least you should have some idea. We'll continue with the topic in the next course, which is water engineering. So for critical depth in a channel, determine the critical depth in this trapezoidal channel for a discharge of 500 cubic feet per second. The width of the channel bottom is B equal 20 feet, and the sides slope upward at an angle of 45 degrees. Okay, angle of 45 degrees. So we want to determine the critical depth. Okay, and to determine the critical depth, this case, we relate to the channel geometry to top width and area. Okay, remember this equation. Okay. And then by iteration, choose y and compute a cubed over t. Then find y that yields a cubed over t equal to 7764. All right. We have this formula for the critical flow, which we obtained by differentiating the specific energy equation and equating it to 0. Okay. Okay. We know the flow rate Q has been provided, G is constant. So when you evaluate this, it's equal to 7764. Now, what is now the depth of flow that will give us? Because this is area, this is top width, okay, for rectangular section. sorry, for trapezoidal section. For this channel, the area of the trapezium, of the trapezoidal section, is y into b plus y. And how did we get the area? Area of a trapezium is half sum of the parallel sides times height. This is the top width. Let's divide it into rectangle, triangle, okay? So this is B here, this is B, but what about these sections? Okay. This angle is 45, okay? So if it is 45, life is made easier. If this is 45, then this angle is 45. It means that if this is y, then this is y also, because it is 45. So the top width is going to be b plus 2y, which is here, okay? And the area is of trapezium is half sum of the parallel sides times height. Parallel sides will be b plus the top width times the height, which is y, okay? Then this is half, b is b, and then t is b plus 2y times y, okay? So this is half, this is 2b plus 2y times y. So you see, these two will cancel these two. So you will have just y into b plus y. And this is exactly how we obtain this formula here, okay? And then when you substitute a and t equal, b is not, the only unknown here is y. So you keep assuming values, you iterate. By iteration, you choose y and see, will it give you 7764? If it doesn't, you change the value of y, either increase or decrease, okay, until it is equal to 7764. And that value that gives you 7764 is the value of the critical depth, okay? It is the value of the critical depth of flow. Now, these are some hydraulic structures in which critical flow occurs. I mentioned the broad crested weir. You can see critical flow occurring here. As a result of the reduction in the cross section, the depth of flow reduces. So the flow is accelerated over the broad crested weir. So the velocity here is higher than the velocity here. Okay, and also flow under a sluice gate. Okay, we will do all these experiments in the lab. We will observe all these shapes in the lab. Okay, in water engineering. This is sluice gate. So here is critical flow, sorry, subcritical flow, and just below the sluice gate you have critical flow, okay? And then downstream you have supercritical flow, okay? And also flow through a venturi flume, okay? This is subcritical within the throat section because it is accelerated to critical conditions, so it becomes critical, and then downstream is supercritical. Okay. And for this section, you see, we introduce you to the open channel flow, but we will also do a lot of things, in water engineering to expand more on the open channel flow, like channel design now, okay? How do you design a channel, okay? Like the channels downtown in Hufflepuff for conveying flood, for conveying rainwater. How do you design it? What are the design criteria? We will look at that in water engineering, and then we will look at the other aspect of pipe design, water distribution network, okay? We talked about the loop, when you have parallel pipe system, okay? So we'll look at a more complicated system, which is how do you design water distribution network. All this we'll treat it in water engineering, okay? So now I'll just give some brief overview about the other chapter, which is chapter 8. And then we take our quiz and go. We have already started talking about dimensional analysis before, because for all engineering courses, you have to talk about dimensional analysis, dimensions. What is the dimension of length, L, dimension of mass, M, dimension of time, T, okay? And we talk about some dimensionless numbers, like Reynolds number. We just talk about the fruit number now, okay? All these are dimensionless numbers, okay? So the dimensional analysis, we have already, let me see what you are writing. Yes, what is it, Mohanad? Okay. No, I haven't seen your message yet. Probably you sent while I've already started the class. Don't worry, we will talk. Let me just say some few things here. Okay. So dimensional analysis is a method to analyze a physical phenomenon. Okay. When there's an equation showing a relation between a number of physical quantities involved in certain phenomena. And the two sides of the equation must be dimensionally balanced. Very important. Fundamental and drive units. These we discuss in statics, even in fluid mechanics, length, mass, time. Then you have those units that are based on more than one fundamental unit, which we call derived units. Okay. And dimensional analysis is a method for reducing the number of complexity of experimental variables which affect the physical system. Okay. And in fluid mechanics, you usually use 4 basic dimensions: mass, length, time, and temperature. Okay. Although its purpose is to reduce variables and group them in dimensionless form, dimensional analysis has several side benefits. First, it is enormous savings in time and money, and second, it helps our thinking and planning for experiment or theory. It suggests dimensionless ways of writing equations before we waste money on computer time to find solutions. Okay, and then it also, the third benefit is that dimensional analysis provides scaling laws, which can convert data from a cheap small model to design information for an expensive large prototype. So we can convert from small model to a large prototype. Very important. Okay. And in dimensional analysis, you try to consider all the factors that affect a given process. Okay. Like you are determining how drag force acting on a smooth sphere immersed in a uniform flow depends on fluid variables, the density and the viscosity. Okay, so the drag force is a function of all these variables. So dimensional analysis will help us design and perform these experiments in a systematic way. Okay, so we can keep some variables constant, vary the other, you can see, versus D versus this, giving us different shapes. Okay, we fix some and vary others. And it's possible to simplify the dependency of drag force on other variables, okay, using non-dimensional parameters. Okay, you can see this is the Reynolds number. Okay, this is the Reynolds number. If you can see it, rho VD over mole. So these are some dimensionless groups in fluid mechanics. We talked so much about the Reynolds number. Okay, we just finished applying the Froude number, which is simply the inertia over the gravity. Okay, which applies for free surface flow, for open channel flow mostly. Okay. In other applications, you will talk about the others: Weber number, Mach number, Prandtl number, and a Peclet number. So you have many dimensionless groups. Okay, you also have Peclet number. Okay, but for now, at least Reynolds number, which we use to classify flow as either laminar or turbulent. Now you know fruit number, which we use to classify flow as critical, supercritical, and subcritical, depending on the value of the Reynolds number. So these are some dimensions of physical quantities commonly used in fluid mechanics. Okay, you have mass, this is dimension L. We write the dimensions all in capital. Okay, for density ml/3. You know, from the unit kilogram per meter cubed. Okay, kilogram mass, which is m. Okay, and then meter cube, meter length, which is L. Okay, so from the unit we derive the dimensions. Very simple. So if you know the units, you can derive the dimensions. And this is for other physical, you know, work, energy, you know, surface tension, and all that. Law of dimensional homogeneity. This we know. Both sides of an equation must be balanced, isn't it? Both sides must be balanced. Pressure, gamma, H. Okay, it has to be balanced. The dimensions have to be equal on both sides. Very important. And there are many methods of dimensional analysis. The techniques have been progressively refined over the years. You have the initial method or the Rayleigh's method. You have the Buckingham-Pi theorem, matrix method, Honseca. And all these methods are dependent on the correct identification of all factors which govern the physical events being analyzed. And in any physical phenomenon, the dependency of a parameter over another is determined by dimensional analysis. In this course, we shall discuss, you know, two, the initial method or the Rayleigh method and the Buckingham-Pi theorem. Okay. Due to time constraints, I will not go into so much details about the dimensions. Okay. But try to take your time and check them. Okay, but at least, like I mentioned, we talked about some dimensions before. You know, the uh, uh, Reynolds number, the um, fruit number, okay, which are very important. So at any point in time you are asked to mention dimensionless numbers, you should be able to do that. Okay. So now um, we will take our last quiz now, okay? And because of what we discussed in chapter 5, I will give you some few questions as homework, just on chapter 5, you know, just to, sorry, chapter 15, because it's going to be part of the final, okay? And for the final, to make things easier for you, I will suggest you should concentrate very well on the homework, okay? Ensure that you study the homework, the solution. All the homework solutions have already been posted. I will await you to, once you submit the homework I gave last week, I will post the key solution. So study the homework very well, understand it. Understand it. I'm not saying you should go and memorize the numbers or anything. Understand the solution steps very well. You know, in the exams, you have to provide all steps. If you jump steps, it will only lead you into some problems, okay? So make sure you provide all the steps. So study the homeworks very well, okay? Study the homework very well, okay? If you really master the homework, all the homework, then I tell you, you will have no problem in the course at all. And the exam is going to be comprehensive. 20% will be from what we cover in the first major, 20% from what the chapters we cover in the second major, and 60% from what we cover in the chapters after the second major. Okay, and the duration is 2 hours. Okay, so I will just post the last quiz now. Okay, so like I emphasize, homework, understand the homework very well. Make sure you understand the homework very well. Okay, okay, the questions, I'm sure that they are going to be simple, but if you study well, you can get 100%, I tell you. you can get 100% in the final exam. And then you remember the final is 35%. 35%. So if you get all the points, it will really boost your grade in the course. It will seriously boost your grade in the course. Okay. So, like I said, I will post the quiz now, okay, on the Blackboard, and then you solve it and submit via my WhatsApp number. Okay.